Very good. Everyone, welcome. Today we're going to talk about Valkey in Telecom and how we use it inside of Ericsson. So my name is David Östman, and I'm a manager in the Ericsson open source division in Sweden. And I'm joined on stage by Viktor Söderqvist.
Yeah, I'm Viktor. I'm a developer and maintainer of Valkey.
Yeah. And we're going to talk about a lot of things today. I mean, first we're going to go through a little bit what Valkey is. Maybe not everyone is familiar with that, so we thought it was good just to give an introduction. A little bit what Ericsson is, because maybe not everyone knows what Ericsson does. Our journey to Valkey, and Valkey in mobile networks, how we use it, and also new features in Valkey. So I hand over to Viktor here, who's going to go through what is Valkey.
Yeah, thank you. Yeah, so if you don't know, it's a key value database. It's focused on very much on speed. We measure roughly in millions of requests per second now. So compared to some other databases, they usually measure thousands of requests per second. It's often used as a cache. It's key value, but it can do other data structures a little bit like that. And yeah, there are some more features. And it was created last year as a fork of Redis. Maybe you know about Redis. It was a famous open source project for 15 years. And then suddenly they decided to change license, kick out the core team, and basically all the contributors left. And we were very quick to discuss with I was one of the active contributors at the time, together with a few more people there. And we very quickly talked together to create a fork. And that's how Valkey was started. So it was a Linux Foundation project after 1 week, and we were really quick to get this up. Yeah, and it's backed by a lot of companies now. And there are more contributors even from other, that's not mentioned here, but these are the official ones that provide their logos. And this is how the maintainers look. We don't have a picture where all of us are actually in the same picture, so we just had fake this one. But the three of us to the left, we are all here. We can find us in the Valkey booth. And we are from 6 different companies, and so to make sure that nobody can just take control of it and do something bad. So it's under Linux Foundation. And the project is thriving. We have a lot of activity. It's roughly 2 commits per day that we merge. And lots of contributors, it was like a storm after this happened. So it's really successful. And then I don't know if these numbers are updated, but you can find other numbers. So this some performance comparison. This is a recent comparison by an independent blog post. It tested the last Redis and this one versus Valkey, and this Redis was also recently from this year version. So none of this is when the fork happened. It was much slower, both of these, and we have a lot of optimizations during the last year, and Redis has been copying what we're doing. That's a bit funny, I think. So yeah, you can show we have improved performance, especially when you use threading for I/O. Because it was designed as a single-threaded originally, but it's evolving to use threads for I/O. And that's what I have to start with. And we'll go back to a bit more about Valkey later, but first about...
We got the crash course in Valkey here. So
yeah.
You will get the crash course in what Ericsson is then.
Yeah.
I mean, few words on what Ericsson is. I mean, we are one of the leaders in mobile networks and 5G. So we provides mobile network infrastructure to mobile operators across the world. If you exclude mainland China, roughly half of the traffic in the world is handled by Ericsson equipment. We have loads of, as you see here, a number of live 5G deployments. If you look a little bit on our portfolio, I mean, we do everything from 5G core to the radio stations, to networks, managed services. We also, with Vonage, then we do API exposure, so the 5G. We do wireless routers, and if you come by our booth, you will also be able to see a few examples of our routers there in the booth, if you want to squeeze on that. But we have a very broad portfolio with many different products. This was a fun picture, so I thought I would add it. We've been along since a very long time. This is from 1876, so this is the founder of Ericsson and his wife working on a telegraph. So we've been around for many years. If you look on the different, I mean, we have been able to invent ourselves many times, reinvent ourselves, all the way from Lars Magnus and Hilda then to manual phone exchange to the mechanical phone exchange. First mobile to digital exchange, and then of course the whole 2G, 4G, 3G, 5G evolution, so to say, where we are now. And of course from the 80s, the mobile evolution has started, and it usually comes with new Gs then every 10-year cycles, from 2G up to, you maybe recognize these old phones that we did once. Now we do more network things. And what we see now is that we move into 6G then, the next generation. That we probably think will be around 2030 will come with the next generation network, enabling more advanced services that XR and cool stuff that will come. Okay, now I will talk a little bit about our journey to Valkey then that you mentioned. I mean, it was a quite abrupt, fast change when Redis decided to change the license then. And we as a big company needed to move fast, so we will talk a little bit about how we did that then and what we needed to do. And I made a fun joke last presentation where I more or less said the same things. I will do it again. There was another guy with the same haircut as me a long time ago, maybe you're too young to remember, that said developers, developers, developers. And I do the same. I mean, it's the keys to success, especially in this Valkey case. I think it was that especially Victor here then was involved in Redis before. And of course, they knew the others maintainers there, and it becomes so much easier, and it was a fast way to get insight, what's happening. And also, you know the code base, you know what we needed from our product side, if it was a good way to go. And without that, I don't think we would have managed to move so quickly in a big organization. Then I invented a new concept here, power of the internal trio, so to say. And I don't see this as individuals, it's more like functions. But when you have the developers, the R&D management, and the OSPO team then. And I think especially for this, we created a task force with all of these represented, because especially in a big company, it's not so easy just to say, let's join. I mean, it's a loads of things that needs to be aligned. Is it strategically fine? Is it approved by higher management? How do we do this? What about our brand? All of these things needs to be sorted out. What is LF doing? What are the other companies doing? But I think we managed to do this in a very quick way, with support, of course, of Victor from the discussions happening there, and of course OSPO and everyone involved. And then why did we in the end choose to join Yocto then? And
Valkey.
Valkey, oh sorry.
Too many projects.
Too many projects. That's a good one. You should do both. No, but I mean, we already have developers deeply involved, so it was quite natural for us to join. And we saw that this offered a transparent and open project, and that's important for us as a company. And of course, hosting this in Linux Foundation, we think that that was good for us to create that type of environment. And we are with Valkey from the start, and we will continue to do for a while. And one important thing is there, I mean, it became a natural split between me and Victor, and I'm mostly participating in the Valkey working group meetings as a manager then. I think it's good to support in that way, and Victor is of course a core maintainer. But it's important for everyone to know that, I mean, you can contribute to projects in many different ways. It's not only developers, and anyone who wants to support Valkey, please go to the Valkey booth and support the project, of course, as much as you can. Some key takeaways then. I mean, I think from the lessons that we learned in this fast moving as a big company, I think to have developers upstream is key, so to say. I mean, very important to get insights and understand for new projects to join. Collaboration is of course key. You have to work tight with the OSPO team, R&D management and developers to be able to move fast in a big company like Ericsson. And we managed to do full alignment, and we are joining and supporting Yocto full steam ahead.
Again, Valkey, not Yocto.
Sorry. And then this is my last thing, I think, for
I think you will. That's
Valkey. Yeah. We have one more thing then. We tried to see a little bit the usage of Valkey in our products. And of course, it can be sensitive then. So this was more or less the picture we got. But we are heavily using it in the 5G core products that we have. And here you see a little bit of how many customers we have in the world. I can't say the names of them here, but you could imagine that many of you are using Valkey when you use your mobile phone every day, when you use Ericsson equipment. And we are all over the globally using this in our products. But Viktor go through a little bit more on how we use Valkey more in detail in the product itself. So I will hand over to Viktor now, because we have a little bit of special requirements. Maybe we are not so like the other operators and so on. Yeah.
Yeah, like the other users of Valkey, perhaps. It's a telecom, it's a bit different field. As you saw, the number of customers maybe doesn't look like very impressive, but these are very big companies, like national telecom operators. And it's a critical infrastructure. It's connectivity for all the other applications. And usually we want 6 nines of availability and very low, very strict requirements on latency and availability. And I should look at this one instead. Yeah. And so we monitor the systems and make sure that we don't have any overload, and where like CPU level reaches like 80% or something, we start prioritizing the most important traffic and ignoring new connections, things like that. And all kind of redundancy backup plans for everything possible and impossible. And I will show you, this is like a picture of a mobile network, very high level. And if you want to learn some terminology, UE is a phone, basically. It can be something else, but it's connected in the same way with a SIM card, whatever. And radio access network is the towers, and there are some connections between them. And then there are many of those as well. And then there's a core network, which is handling like where each phone is, which connections it has, if it's idle or if it's active currently. Most of the UEs are idle most of the time, because the radio bandwidth is very precious. And so if it's idle over like a few seconds, this radio channels are taken down. And then once it needs to send some data, it sets it up again using this tells the control plane that I want connection again. And so there's a split between the control plane and the user plane. User plane is the user data that the user needs to send to the internet or get from the internet. It can be incoming data as well, like incoming calls, push notifications, whatever, and then gets. So I can go into the different roles there. There's the user plane function. It handles, it kind of keeps the IP address of each of the phones, because they are not really plugged in all the time. They are most of the time idle and somewhere moving. So when there's an incoming call, incoming data, UPF notifies the control plane, AMF, SMF, and then can broadcast to find this phone, which is in the known area, more or less known, because if it leaves the area, the UE has to tell the network where it is, so it can be found. So and if it moves to a different country, different state, it also notify. So even if there's a different, so this for example, the AMF is the mobility management function, and it's supposed to keep track of where the phones are. So if you move to an area covered by a different AMF, these two can communicate and transfer session data and a lot of data between them. So we don't need to do like full handshake with the phone again, which we avoid because it's a lot of overhead and the radio back and forth ping pong. What's it called? Round trips. That's a very short crash course on mobile networks. So many of these, they don't have persistent storage. They don't need it because like the UDM there, subscriber database, it has like the persistent storage of the subscribers. And that's separate entity. And all these roles are standardized, and the protocols between these ones, lots of things are standardized in telecom standards. So even if these are from different vendors, everything works together. I have drawn there some circles around which ones are Ericsson products, if you want to buy one, and maybe, I don't know, just in case. There's the packet call control and packet call gateway. And I know for sure that these are using Valkey in some way. And I will go into how one of these could work internally, because it's like I cannot really tell you how it works, but hypothetically. They run in Kubernetes clusters, and Valkey is like, it's not too different to like a web application or something like that. But Valkey cluster is just a microservice within the application. It's not something external. Like if you're using some host managed database as a service, that's something external to your application. But here is like internal part of the application. And yeah, there is some kind of load balancer. There are application pods, multiple of them, and we make sure that the same traffic for the same user goes to the same instance all the time. So we can do some smart routing there, which is I can show you later what's the benefit of that. So we use the setup of a Valkey, which is called cluster architecture. You can run a single node without clustering or without any kind of replication. It looks like this. So there's replication for redundancy, and there's sharding for horizontal scaling. And each of these clients connect to each of the shards, because some data is spread out on the shards. And that's basically the only way you can set up Valkey so that it scales and you have full redundancy, high availability. And inside one of these instances of the application, we have a lot of concurrent tasks going on for lots of different phones. So let's say one of these tasks, each of the tasks is handling some operation, some procedure for a particular user. Let's say it's moving between two towers and you need to coordinate that, and to make sure that it doesn't have a glitch when you have an ongoing whatever, streaming something. There's no glitch supposed to happen. And there we have some communication to the Valkey nodes. We use a lot of pipelining there, which means each of these tasks can send requests. They are just routed to the right Valkey instance, and then we just send a lot of them. And then the replies come back in the same order. And so that's a very good thing with the pipelining, that you can just send stream request, the replies come back, and they get routed back to the right place. And you can see, if you can understand the colors of these arrows, or what I mean. So we don't need a connection pool. We just have one connection to each node, and that's it. Just using a lot of connections, it's just more work for the Valkey nodes, and yeah, just more overhead. Doesn't make any sense. Just Valkey nodes handle one command at a time anyway. And we also have an in-process cache, which is even faster than Valkey, which is over the network. So this is just basically a thread-safe hash table inside the process itself. And so the application can work even if the Valkey is down. For example, if one of the nodes is failing, it takes a few seconds before a failover happens, and then another node takes over. So during this time, we can still handle traffic, because most of the time it's already in the cache, internal in the application. And this means also that we have most of the traffic to Valkey is writes, because most of the reads are already cached. So in this way, we are using Valkey kind of as a backup, not as a cache. Which most people use it as a cache and use some other slower database as the backup or something. Yeah, hope that's it. And now we go into some new features in Valkey recent versions. For that we'll talk about 8.0 and 8.1, just very few, very short. And one of the killer features for Ericsson is the possibility to downgrade. I'm sure that nobody else will mention this as a new feature, because it's like, what the fuck, who wants to downgrade? But we do. Of course, you want to do a rolling upgrade, and then when you do that, that's nothing new, but that it just works in a similar way. When you do a rolling upgrade, you add replica, attach it to a primary. So the primary gets all the writes and it's replicated to the replicas. So you add, in this example, you add two new replicas, and they synchronize and replicate the data. And then when they are in sync, you can do a switchover. And then one of the updated nodes is the new primary. And then the old primary is now a replica. And then you can remove those old version nodes, and you have an upgraded these nodes. The new thing is that we can also do this for downgrade. Why do you want to downgrade? Well, if you upgrade and you notice, so our customers run this in their own data center. That's one thing. So they can, and it's as an internal part of the application. So even if there's nothing wrong with Valkey, there may be something in the application itself, the telecom application, that you notice, like some too much CPU load, I don't know, something that I worry about. So then our customer can downgrade, can decide to downgrade, just to be sure that nothing is going to happen. And yeah, that's a new thing, Valkey 8.1. For that, just exactly the same procedure, but the difference is that the old replica needs to be able to read the data from the new primary. The newer version primary sends data to an older version replica. It has to be able to understand it. So the contract we have is just like, as long as you don't use any new features, the data should be possible to understand by an old version replica. And that was not obvious. It was never supported in the past. Yeah, and another feature is dual channel replication. It came in 8.0. That's in September, I think, last year. What's that? Dual channel replications. What you have two? Why is that? We'll come to that. So replication is when you get some clients, they set some data, set some key to some values. Asynchronously, these get replicated. They just sent over to the replica. And I hope that's pretty easy to understand. But when primary already has a lot of data and the new replica comes in, then you need the primary needs to transfer this, like a snapshot of all the data. And at the same time, lots of clients can continuously send a lot of changes and writes. And these as well need to be forwarded, so that we set up two connections, one to transfer the snapshot and another one for the continuous stream of changes. And that offloads the primary a lot previously it had to buffer all that data until the snapshot was transferred. So it doesn't have to do that anymore. It's a very sensitive time when a new replica comes, because it's extra load, and that's always a critical point in time. Another area we've been optimizing is performance and threading. So here is traditionally it's been a single-threaded application based on event loop, where you basically use ePOL to listen to a lot of sockets if any of them has any incoming data, like any reads or writes that are available, and then you get like a set of file descriptors where you can either have some reads or writes, and then we do the reads. We process. We parse this is like a command and handle this command, and then we send the writes as much as possible, as much as we can to the socket, and then we go back into the EPOL, which is blocking. And we notice that the I/O takes most of the CPU time, like the reads and writes. You see there more than half, more than 50% of the CPU time. So we wanted to because the command processing is single-threaded. That's the way we keep the consistency, which we don't need a concurrent multi-version concurrency for the data records, like some SQL database use. So there's a possibility to use threads for the I/O, and it looks like this. We have a main thread that still handles the commands execution and does EPOL, but in a non-blocking way. So we just spin there, and when we have some I/O jobs, they are sent to the I/O threads through a non-blocking queue to each of them, and then they can just handle read and writes, and also offload, do other things like parse commands, do some preparations, and do TLS handshakes. We have been gradually adding jobs that I/O threads can do to offload the main thread, and this is a new design that was improved, and as the benchmark result I showed in the beginning, it's just thanks to many of these things. And another thing we've done is to replace the hash table, which is like the data structure that stores the mapping between keys and values. So it's like a very important part of a key value storage. And there are some examples there. The key can be like some code, and the value can be something else, like I don't know, the city where this conference was. And the hash table used so far in Redis and Valkey was a basic one that, like in a computer science course. I can show you how it looked like this. A hash table is basically an array, if you don't know. And the key is it's hashed. It's a hash function that basically it turns a key, some string into a number, and this number is interpreted as some kind of index into this array. It's in some semi-random way. So two keys can map to the same index. It can happen. I mean, it's not possible. It's impossible to prevent it. So if it happens, so that's the place where the key and the value is supposed to be stored. So if two of them are in the same place, they form a linked list just to resolve this collision. And then the key value are pointers to separate allocations, and then there is a next pointer to the next entry. And this means it's a few pointers to follow and a few memory accesses to actually get the keys and the value out there. And we think about how to optimize it for speed and lower memory usage, and that's basically to reduce the number of pointers you have to follow, because to access memory that's not in the CPU cache is the slow part because memory access is a slow thing. We don't have any disk accesses, so we're optimizing just trying to have things in the CPU cache and have fewer memory accesses. So to reduce the number of pointers, we wanted to design it in a different way. So the new design looks more like this. It's we instead of having a single element in an index, we have a bucket of some slots where we can store, like if there is a collision, we just store them next to each other in the same bucket. So the bucket is a cache line size. So when the memory is loaded when some data is loaded from main memory into the CPU cache, it's done in the blocks of a cache line. So when you access the first one, you automatically load the rest of one in the same bucket. So if the first, and then this key and value can be stored, like let's say foo maps to the value bar, and if you want to look it up, you get to this bucket, and so how do you know if it's the first, second, or up to the next one? So we have a secondary hash function. In this case, I just used the first letter of the key, which that's not how we do it, but just it's easy to understand from the drawing. So that means like we store that as well some metadata into this bucket, so we can check, like if you're looking for buzz, we can say that okay, the first one starts with F, can't be this one. Maybe the next one, start with B, probably that one, and then we can reduce the risk of looking at the wrong key. So in this way, we can just have 2 memory accesses. One is the bucket, and the second one is the entry where the key and the value are embedded in the same allocation. So that saved us roughly 2 bytes per key and some performance. But the performance can be avoided in other ways by doing memory prefetching techniques. So we didn't see a lot of speed improvements, but we save a lot of memory, which is also very important if you have a lot of small keys and small values. I don't know if that is it possible to understand? I hope so. Otherwise, you can. Yeah, we have to speed up. So this is a possible, when there's a collision, we have like some chain linked list anyway. I will skip that for now. The exact memory layout, I'll skip that as well. And yeah, a summary. Yeah, you can contribute. Do you want to say something about summary?
Sure, I can summarize. I mean, you want to? No, but I mean, Valkey is a critical piece of technology. We encourage all companies to participate and support. Engage in Valkey today. I mean, you can see here the links to GitHub and the website if you need more information. You can go to the Valkey booth.
And the Ericsson booth.
And the Ericsson booth, where Victor will be
We'll be around
you,
there, also the booth.
everyone.
Yeah.
So with that, maybe we can see if there are some questions from anyone. Yeah.
So you said that Valkey is used mostly as cache, which we got that. What is the next most popular, other than just like gets and sets? What's the next most popular use case? Do you find hub sub to be a huge popular use case, or do you find like sorted sets to be more popular than hub sub? Like what's the second most popular use case?
Okay, so I repeat the question. So what's, apart from get and set strings, what other features are the most popular? I mean, we don't really know. In Ericsson, we use it for our, I guess these service providers, they have more statistics about what users use. But there, I suppose there are sets. I mean, the key is always a string. The value can be a string, or it can be a set, or another key value sub-mapping, or a sorted set, as you say. I don't know, to be honest. And there is pub sub. There are various features. I don't know really which ones are more popular. I guess it's when we run benchmark, we often run get and set. It seems to be the most basic usage.
Yeah, I think job queues is usually like
Job queues, and we also have the expiration. You can set expiration on the key, so it disappears after some time. That's probably used a lot in caching. And yeah, I cannot really say what's popular. It's used a lot now to cache like a language model, like AI, training data, prompt caching, things like that. There are new use cases coming up.
I don't think we have time for any more questions, but we are available on the Valkey booth or outside after this session.
We can take questions afterwards. Yeah,
so please, thank you everyone for coming, and I hope you had a good presentation. Thank you a lot.